Okay, so what I have here on the screen are four lines in the plane, black lines, and the 2 points associated with them. Okay, an internal one, which is the intersection of these two internal diagonals. There are going to be 6 total intersections, right, between these four lines. So you have this L sub I, and then I have an L sub B, which is the foot of the perpendicular dropped from L sub I onto this outer diagonal here, connecting these two outer intersection points, Q and Q prime. Okay, so this is pretty well defined. I can play around with this complete quadrilateral, okay, changing its shape, but I'm going to have this phenomenon here dynamically well established. Okay, so I can just move these four lines at will, and I can always compute these names, these points. Now, why are these called L sub I and L sub E? That's because they're related to the concept of limit points, the internal limit point and the external limit point. And you talk about limit points when there are two conics involved. So first conic here would be any inconic to this object here, this L sub I, and another conic would be any circumconic to these 4 points here. So if you pick any two such pairs, an inconic to the 4 lines and a circumconic to these 4 points here, both of them are one-dimensional lines, it turns out that their two limiting points are invariant over those choices. But this is not what we want to focus on right now. I just want to focus on this very simple construction. Start from 4 lines in the plane and get L sub I, intersection of the two internal diagonals, and then you get L sub B, the foot of the perpendicular drop from L sub I onto this outer diagonal here. Okay, now let's now switch to Poncelet world. Let's see if I can do this. Okay, here we have a Mathematica app where I am showing an n equals 5. Well, let me switch to Mathematica. An n equals 5 bicentric family. Okay, so n equals 5 meaning that there's 5 points in my Poncelet family, so it's a family of pentagons. Now this is interscribed between two circles, and this is called the bicentric family in reference to the fact that this is a bicentric polygon. Now of course I can gyrate this family at will. We've seen this exhaustively in previous videos. Okay, here's the center of one of the circles, and here's the center of the caustic. So this is the center of the external, here's the center of the caustic. Okay, now I want to repeat that construction that we just showed, right? This construction here. However, this construction involves 4 lines. Now, Poncelet N equals 5 has 5 lines. So what am I talking about? I'm going to pick, so if you take 5 lines which make up this Poncelet family, I can connect P1 to P2, P2 to P3, and so forth to get 5 lines, infinite lines. I can take them 4 at a time. So when I take the first set of 4 lines, let's call them P1 to P2, P2 to P3, P3 to P4, and then I'm going to close this first quadrilateral by considering the line not a P4, P5, but a line P4, P1, right? So I have 5 such combinatorial quadrilaterals if I take a collection of 5 lines with 4 at a time. So this polygon here is associated with 4 complete quadrilaterals. Now here's what I can do. I can repeat that construction. For example, taking the first 4 lines, okay, and I can compute the intersection of those internal diagonals, so from P1 to P3 to P2 to P4, so I'm getting this first point here, right? And then I can repeat these internal diagonals 5 times for each of the combinatorial quadrilaterals, taking 4 lines at a time, and I'm going to get line internal points, internal LIs. I'm going to call them L1 because some first vertex is omitted. L2, L3, or 5. These 5 are going to, by definition, fall on an ellipse. Now it's interesting that when you gyrate Poncelet, this ellipse is fixed. Now this is a known result. It goes back to a paper by Tabashnikov and Schwartz, where they basically say that the locus of intersections of diagonals are in the Poncelet family, and these are valid diagonals of this Poncelet family. They're going to describe an elliptic locus, right? And their locus is going to be an ellipse. So there's nothing really interesting here. You can see that this ellipse is stationary over Poncelet, but interesting things happen when you start looking at the outer, right? Now what do I mean by outer? when we start looking at, going back to that other image, when we start looking at the locus of these outer points here, okay? These outer limiting points, if you will, or this foot of the perpendicular drop from this point to LD. So let's draw one in our Poncelet setup, okay? I'm going to draw one of them. I'm going to draw all of them, okay? And let me actually draw the construction as well of this point. So to draw this construction, I do this. Now let's see if we can make sense of what's going on here. If I turn this again a bit, we can see both Q's. Let me scale this down a bit. Okay, so you can see here that I'm dropping a perpendicular from this intersection of diagonals onto that Q prime outer line. This is actually the polar of this point L1 with respect to the caustic, to this inconic, okay? So I'm getting this point over here, right? So you can see here that you have these intersections here, Q and Q prime, of the outer, this is the outer diagonal of the quadrilateral formed by P1, P2, P3, P4. Okay, so I can repeat this construction 5 times and certainly draw a conic, in this case it's an ellipse, to the 5 external limiting points. Okay, so let me remove these construction lines for now, and now we kind of get a picture of what's going on here. Okay, now the first thing we notice is that when I make Poncelet turn, that outer conic is not fixed. I'm actually reporting in here the ratio of their axes, okay? And you can see here that the outer conic is actually undergoing some, you know, what would you call that? Like, you know, focal length changes. Okay, and just aspect ratio changes. And nothing's fixed. Its foci are moving, probably an interesting loci. I have to draw those. And its center is also moving. Well, let's try another family. Let's try now the confocal family. Now let's center that on the screen. And you can see here that something interesting happens for the confocal case. I'm repeating the same thing. I'm just taking 4 at a time out of these 5 guys. I'm computing the inner limiting points, which are the midpoints of the diagonals. For example, here I'm only considering P1, P2, P3, P4. So these 4 lines, 1, 2, 3, and the 4th line is going through P4 to P1. Okay, so I have this polygon here. I'm computing this intersection. Okay, and then corresponding to this intersection, I'm computing a point over here, which is, let me see if this thing is stable. This doesn't seem to be very stable. Let's see here, scale. Yeah, so I have that outer diagonal there, Q to Q prime, and I'm dropping a perpendicular which is coinciding in this case here apparently with one of the 2 endpoints of that diagonal, which is fine, and that's why I'm getting some instability here. But the interesting thing is that the collection of these outer guys, okay, over here, collection of these outer guys is falling on an ellipse which is stationary over Poncelet. This is different from the previous experiment, right? And it also seems to be confocal, with a confocal pair generating this Poncelet family. How do I know this? Because its foci are shown here green, are lying exactly on the foci, so if I turn this off, of my original Poncelet pair, which subtends this confocal pair. Okay, so here's my confocal family, right? The billiard family, whose perimeter is conserved. But now when I'm drawing those outer limiting points, I see that, and this is for n equals 5 exclusively, okay? They fall on an ellipse that is stationary and whose foci, green and green, are confocal with the original pair. So this is pretty nice. Now here's for the nicest phenomenon that I want to describe in this video. And this has to do with something that I'm calling the MacBeath family. Now let's look at the MacBeath family. What is a MacBeath family? Let's scale this up. The MacBeath family, and this is n equals 5 MacBeath, is one that is inscribed in a circle and which circumscribes a caustic for which one of the foci, F1, coincides with the center of the outer circle. So here's one of the foci of this caustic, brown. Here's a second focus, right? And here's the center of the caustic. Okay, now I do have a 1D family that I can choose from. In every single case I have a 1D family modulo, some rotations and scalings. But here's one particular instance of this MacBeath n equals 5. Okay, of course I can do what I did in the past, which is just gyrate. Now first phenomenon which we notice here, which is quite harmonious, is that the 5 internal LIs, they fall on a circle. Okay, so this is the only family for which I've seen this, only sort of natural or canonical Poncelet family, for which I see these 5 guys falling on a circle. They normally fall on a stationary ellipse or conic, if you will, but here they're falling on a circle. So there's something very special about this family. Now let's look at the external guys. The external guys also fall in a circle, and that's quite surprising. Look at this. And this is a stationary circle, right? So I haven't seen this in the bicentric case, for example. In the bicentric case, which I'm showing here, both cases, internal and external, fall on ellipses, of course. Well, I'm drawing an ellipse through the 5 points, but the external case, the ellipses are not, the ellipse, the green ellipse, is not fixed. Now I'm still curious to find out what the locus of these foci and of this center might be under the bicentric case. Okay, they look pretty interesting. Okay, it could be that they are circles. I'll report this on some future video. Okay, but what's really awesome about the MacBeath family, okay, is that both the LIs, the internal ones, and the LEs, the external ones. So here's a particular construction for this external guy here. Okay, I'm taking L1, I'm dropping a perpendicular onto, as we said before, onto that line of, onto this external diagonal. Okay, so the construction is correct, and basically this is the phenomenon that I wanted to make this video about. These two circular, these two circles of 5 points, right, that are only obtainable under MacBeath n equals 5. Now, just leaving a note that whenever you have n equals 5 on Poncelet, you're dealing with vertices that are very hard to parameterize. Okay, I believe that they are roots of quintic or sextic equations. So this is I would say, an algebra geometric surprise. All right, thank you very much, and I'll see you in a future video.